I'll get this series started. So my name is Neha, and I work at AWS. And essentially, today I'm talking about how we are making verification the new normal for all AWS customers. And to start, we actually extended the definition of verification itself. So we want to enable millions of AWS customers to prove correctness of their systems with respect to their specification. So today, customers can go to the AWS console and use compute, analytics, storage, and database services to build applications, store data, and even run their workloads. And access to all these services and resources in AWS is governed by policies written in a domain-specific language. And customers actually have requirements around who should have access to what. So we go, okay, policies seem like a great verification target. So how do we get the specification? We can't get millions of AWS users to write specifications, though we did try, and it didn't go so great. The key insight is we need to infer specifications automatically, but do it in a way that is customized to each user themselves. And the first application of this that I'm going to talk about is block public access. It's a preventative control, and it's verifying whether a policy grants unrestricted public access to untrusted entities. And how do we get this set of untrusted entities? They can be different for different users. Again, we can't expect them to write the list and the set of untrusted entities and provide it, or even go back and annotate all the legacy policies to say what is untrusted. So let's look at an example to dive into what do we mean by untrusted entity. So here, the username admin is an untrusted entity because anybody can create a username admin in their account. But the source VPC ABCDE is a trusted entity because its value, it's based on an identifier of your private network, and it's set by the system. So our insight here is that we can automatically infer the trusted entities from the policies themselves. And coming up with a precise definition of what these trusted key value pairs are actually requires significant domain expertise and knowledge and work. For example, the value of this source VPC, if it was a wildcard, then it would not be a trusted entity because it's saying allow any source VPC. But even though it requires all this extensive knowledge, it needs to be created once and can be used many times. So once we have these, the next thing we do is we take our policy and turn it into an SMP formula using a tool we have called Zelkova. And here, the set of all satisfying assignments in the formula correspond to the set of requests or accesses that are allowed by the policy. So a request is allowed by a policy if it matches one of the allow statements and doesn't match one of the deny statements. And then finally, to evaluate whether the policy does grant unrestricted public access, we check the satisfiability of this formula that says, is it allowed and is it part of one of the untrusted entities? So, and you can read more about how we do it in an upcoming FSC paper. But the key here is it is integrated into Amazon S3. And this integration needed to satisfy the operational requirements of S3, security, availability, robustness. The other key here is the computational complexity of the problem makes the pathological cases unavoidable. And to maintain soundness, we choose to fail closed, which means if the analysis returns unknown because the analysis timed out, we say the policy is public. So this is great, right? Like, so how do we take it a step further? And taking the idea of inferring specification to the next level is what we did in Access Analyzer. Here, customers want more granular capabilities, not just public access, but they want to say, does an external entity X have access? And we can't, again, expect them to write bespoke specifications. Does Lee have access? Does Nathan have access? First, you have to think about, oh, do I even know the people that I want to be able to ask access to? So what Access Analyzer does is it removes this upfront work of having users to write the specifications to say, ensure that Lee does not have access. In fact, it generates findings to tell you, hey, Lee has access. Did you intend for that to happen? And now it's flipped your notion, because instead of you having to think and write about this, you're given this very declarative statement and you can say yes or no. And it captures your intent into the specification, and then you can use this tool. And the thing is, you can read how we did it. Like we use techniques from predicate abstraction, and there was a talk yesterday by Andrew Gasick who presented this work, and you can read more about it in the paper. And these tools really resonate with customers who can leverage the power of verification without needing to be an expert in the area. And before I wrap up, I just want to provide you something that we are working on right now, and that is to say, how do we even synthesize permissions from the get-go? And this is an example application that operates on an S3 bucket, making a few API calls, and we do a data flow analysis to automatically extract the permissions needed by this application. And here, you can essentially get the right permissions to begin with. So the takeaway here is to make verification accessible to millions of AWS customers, you really have to think, how can we extract, infer specifications, which to them is their intent, and make it customizable to their use case and make it available at scale, where they don't have to think about what they're saying or asking, but it is integrated in their regular workflows. So if this is exciting, we're hiring for internships, full-time positions, and you want to have an impact, work with millions of AWS customers, email us, email me, email this other email on CAP 2020. So there's also this work I talked about, like how AWS is doing verification, but we have equally exciting work going on in Prime Video on how formal verification is being used. So I'm going to hand it over to Jim Christie, who manages a team in London, UK, and we'll tell you all about the work there.
All right, thanks very much, Neha. I'm going to try and take over the screen. I'll do that. Take over. All right, perfect. Hopefully you can see my screen. Just going to get into presentation mode. All right, cool. So my name's Jim Christie. I'm a software development manager at Amazon. I've been in Prime Video for just over 8 years. So I'm not an applied scientist. So if you do have questions at the end, please make sure they're easy. So in the time that I've been at Amazon, I've managed a few different kinds of teams. I started out managing back-end service teams, and then I moved over to manage a native client team. And now I'm managing a really different team, an automated reasoning team. And my team's kind of unique in that it's got a fairly even split of software engineers and applied scientists. And so when we started the team, we decided that we wanted to, have software engineers collaborating with applied scientists to help them build, production quality software that would cope with Amazon scale problems. All right, so first, what's Prime Video? So Prime Video is a global streaming video service, and we offer subscriptions and paid for on-demand content across the world. And our customers use a range of devices to get to us. So they use mobile devices, they get to us via the website, and they use what we call living room devices. So these are things like smart TVs, set-top boxes, consoles, and streaming sticks. All right, so Prime Video is really focused on delivering high quality software, and we use a range of techniques. So we use test suites, we use full CI/CD pipelines, we have device testing labs, we have our own client UI testing frameworks that we've built ourselves. And now, after speaking to Byron Cook, we're now using static analysis as well. We kind of decided that it would be great to be able to improve quality without having to write more tests. Now, don't get me wrong, I'm not saying there's anything wrong with tests. We really do value tests, but we also recognise that they're quite expensive. So this picture on the screen now is the test pyramid, and some of you might have seen this before. And the basic idea is that you should put a lot of your investment into unit tests, because they're fairly cheap to write and they're fairly easy to maintain. And then you should have a healthy chunk of integration tests, and they're a little bit harder to do. They're a little bit more brittle, harder to maintain, a little bit more expensive. And then at the top of the pyramid, you have manual tests. These are really expensive. You need a person to actually run the tests and click on buttons, and they can take a long time, and they can really slow releases down. So we try and avoid those at all costs. But with static analysis, what we wanted to do was to take this goal of compressing the test pyramid and complement traditional testing. And our sort of main aim with it is to automatically catch issues before they hit production. All right, so I wanted to show you a very simplified view of the Prime Video software stack. So what we've got here at the bottom is the customer's home, and in the customer's home they have a fancy TV or a console, and on that device is our native UI rendering and playback framework. And this is responsible for things like storage and crypto and DRM, rendering and playback initialization. So when the Prime Video app starts, what it does is it pulls down the latest JavaScript client from the Amazon cloud. And that then starts communicating over the public internet with the orchestration layer and the backend services, and marshalling and proxying all sorts of different requests for content and UI layouts and things like that. All right, so that's a little overview of our stack. And then, so some of the challenges that we face, delivering our app to millions of customers are, the native rendering framework is very hard to update. It ships with the devices from third-party manufacturers to the stores, and to put an update out to the native client sometimes involves us negotiating with a third-party device manufacturer. So this is really mission critical code. We don't have the option to just roll it back. It's not like a back-end service. We also have, our app is now on thousands of different unique device types, and it's not just hard. It's impossible for us to manually test that every change works with every device. It's just not possible. We have hundreds of software engineering teams just in Prime Video, and we have kind of over 1,000 software engineers, and they're all effectively working on the same product. Now, these teams have done a great job of kind of creating architectural boundaries, but when one team makes a change that another team doesn't expect, it can result in a bad customer experience. And of course, at the forefront of our minds, and I've got it in bold, is we want to keep our millions of customers happy. All right, so how do we do that? So Amazon's overall goal is to be Earth's most customer-centric company, and what we do, we like to help us sort of focus on building the right things. We have this mechanism called working backwards, and the idea is that to start building solutions, we really need to make sure we're solving a real problem, and we do that by actually trying to speak to our customers or get into our customers' mindset. And for my team, we're really lucky because our customers are other software engineers, and we can just go and sit at their desks and ask them questions. So that's what we do. And that's what we did when we started the team. We went and identified some real problems that our engineers were facing. So once we've kind of defined a solution, we can ask the customer for feedback. Does it really solve their problem? Then, of course, it gives us the confidence to then go and design, develop, deploy software that fits the bill, that we can then track, measure, and improve over time. All right, so what is the problem we're solving? So there's a couple, but overall, we're trying to maintain this really high quality bar for our software so that we can keep our end customers happy and prevent them having bad experiences. So static analysis is great at catching bugs, which is really hard to write tests for, but it's actually very hard to mechanize static analysis. It's hard to get teams to fix backlogs of issues. They're really busy, they've got big roadmaps, they've got lots of things to deliver, and it's just really hard for them to prioritize fixing code, fixing problems in the code, which has probably been in the code base for a long time. So we think there's various sweet spots within the developer workflow, starting with local command line tools, and then in code review analysis, and then in the CD pipeline quality gates. And so my team decided to start with the code review as our sweet spot. And so we built an automated code review bot called Bugbear. And what Bugbear does is it listens out for customer code base changes, listens for code reviews, and then it pulls the code and builds it and sends it off to Facebook's awesome Infer. And when we get the analysis results back from Infer, we chop it up, compare it with the diff, and post it back to the code review as comments to say, hey, here's a race condition, or here's a null pointer exception. And this works really well because the developer has the context. They're incentivized to fix the bug before it gets pushed out to production. And we chose Infer because it's really easy to use. It's easy to integrate with, and it biases towards less noisy results, which equals less angry engineers, which equals more bugs get fixed. So we're not just using Facebook's Infer. We're also building our own custom analyzers. So we built our own product called Coast Guard. So this is what the applied scientists in the team have been busy with. And Coast Guard's kind of looking at so Coast Guard's already also run by Bugbear and also listens out for code reviews. It's looking for different things. It's not looking for null pointers. It's looking for results that are very specific to Prime Video code. So we're looking for integration bugs between different architectural boundaries. So there's these critical points in the stack where these teams integrate with each other. And so we built our own analyzer to reason about that integration in the different layers of the stack. So we decided to start out with our mission critical code, which I introduced you to before. And the view that I showed you before isn't quite the whole story. So we have this native UI rendering and playback framework. And to get it onto third-party devices requires third-party assistance. Sometimes we do this within Prime Video, but mostly we work with third-party manufacturers to integrate our app with their device's OS. So we have a bunch of instructions that get passed between the device's OS and the Prime Video client, and they need to be in the correct order. They need to be, they need to be sequenced correctly, and sometimes they can be long running. And that's really hard to test. So we decided this was a perfect use case for static analysis. So this is the bit that we're reasoning about, so it allows us to tell developers whether they got the sequence right. And we call these sequences contracts because we're really kind of enforcing API contracts with these results. And so right now in this layer, we have 9 different contracts that we check when third parties are integrating with our app. And so for example, we do things like we check that global variables aren't being tampered with. If a language or a locale or a time zone gets changed and a comma gets introduced somewhere, well, the bad kind of things that can happen when those unexpected nuances change. We also look at things like callback functions being implemented correctly, which is hard to write a unit or an integration test for. So Coast Guard helps us accelerate the integration process. It helps third-party teams. It helps us get our app on more devices quicker and at higher quality. All right, so what's next? What's next for Coast Guard and Bugbear? Well, for Coast Guard, we're extending it to make more checks across more areas of the stack. There's all these hundreds of teams have all these integration points with critical dependencies on each other, and we want to leverage this reasoning all over the place. And we're also beginning to empower developers to write their own contracts, so they can reason about things. They understand the code better than we do. So that's going to be a huge piece of impact for us to have. And then as for Bugbear, well, so we're going to be adding more analyzers, not just off-the-shelf ones, but building our own custom analyzers. And so, so here's a call to action. So if you're maybe you're developing an analyzer that we could integrate with, we'd definitely be interested in hearing about your analyzer and if it can help us, keep raising the quality bar. We really do feel like this is the tip of the iceberg for the amount of impact we can have using these kind of techniques at Prime Video. I'm not sure if I've got time for questions. I probably ran over a little bit. But if anybody has any questions or has posted any in the chat, I can't see the chat, so I'm going to stop sharing my screen.
And we'll also have, at the end of the session, if folks want to ask questions to any of the speakers, please. And even just another reminder for people who may have joined late, please feel free to type in questions, and some of the people who are not speaking, we can field them, or we can wait for the speaker at the end. So thanks, Jim. That was great. And moving up the stack a little, just we also have another code analysis talk by Lee Pike, who's a principal scientist in Code Guru, and he's going to talk about how they're using machine learning and program analysis together.
Great, thanks, Neha. Can you hear me and see my slides?
Yeah.
Perfect. Okay. Yes. So thank you. Yeah, I'm a member of the Code Guru team, and what I want to what I want to do is first of all tell you about our vision for bringing machine learning and automated reasoning to the DevOps lifecycle. So, we're all fairly familiar with this, how we develop applications and write code. So, you write code, you submit code reviews, we build and test, we deploy the code, then you measure it, you instrument it, make sure that the performance is what you expect, and hopefully this results in a virtuous circle where we keep improving the application. Now, it's easy for me to write this workflow on a slide, of course, but this is really difficult in practice to get this right. So it requires both deep expertise all along here, as well as there's a lot of tedious work to do. So you want deep expertise to review your code, make sure that there's no issues in there. Instrumenting, monitoring your code can be quite tedious, but you also need that deep expertise to take the results of that and understand where that, how to improve the software based on that. So based on that, I want to talk about two services that we have today to address these issues that bring machine learning and automated reasoning to assist developers to provide that expertise and remove some of the tedium. So very briefly, let me mention Code Guru Reviewer, which helps you automatically find and improve the performance of your code by finding hotspots and helping you understand how to remediate them. And Profilers built using machine learning to help automatically improve the code based on this dynamic analysis. However, what I want to spend my time focusing on, though, is Code Guru Reviewer, which operates at the beginning of this DevOps lifecycle. So this helps find and remediate issues in your code at code review time. So everyone's familiar with this workflow. You make a code review, and you have a pull request, or and you have other members of your team look at your code and help you try to make sure you're following best practices, that there's no security issues, that you're using the code correctly. And so you can think of Code Guru Reviewer as an automated additional reviewer that has been specially trained to find hard to find issues. So it's been trained on millions of lines of Amazon code, open source code, to find specific code patterns and kinds of issues that developers might make and help you remediate them. In particular, one thing we've really worked hard on is reducing the noise and false positives. You don't want to wade through a haystack looking for a needle in terms of findings. And so both machine learning and applying that automated reasoning can it helps really reduce the number of false positives so that the recommendations are actionable. And of course, this improves with developer feedback, and the breadth of the recommendations that you get continues to grow as the tool develops. So today we support Java and support Amazon Code Commit, GitHub, including GitHub Enterprise and Bitbucket for repos that you could associate with. So I just want to spend a few minutes just giving you a sense of some of the kinds of recommendations that Code Guru Reviewer can provide today. So here's an example where a developer may be using a concurrent hash map. So suppose repo is a concurrent hash map. And in the second if statement, I'm going to ask it contains a key IP, and if so, get that key. And what can happen is if this is in a concurrent program, another thread may be modifying the map after I check that the branch condition. And if so, I could have a deep, difficult bug that's hard to find because this only happens in a certain instance when another thread's operating at the exact right part of my program. So these are the exact kind of things that are really hard to debug that Cougar Reviewer can help you with today. So an example in a different domain is sensitive information leaks. So here's a AWS API, update job status, and it can take a number of parameters, and update job status may result in an exception, so we're catching those, and that's good. But one thing is that one of our parameters is this the result of get AWS account ID. And this is something that may be sensitive and that customers don't want to log in when they're catching an exception. And so Cougar Reviewer can warn you about this, and so that you can follow best practices in terms of redacting potentially sensitive information. So I've given 2 examples for these first 2 categories, but there's several other categories with numerous recommendations that Cougar Reviewer provides as well. So including best practices across AWS APIs, ensuring that you are handling your resources correctly, that you don't have resource leaks, finding other code defects that you may have, help with refactoring, so helping find similar lines of code across your code base to clean up your code, as well as input validation. And not only is the number of recommendations growing, but also the kinds of categories that we check. So just to give you a concrete example, here's what a recommendation might look like in Bitbucket. So you can see that a recommendation is just like you would see from your other colleagues who are reviewing your code. It provides, it shows you exactly where the issue is, explains how to remediate it, and provides additional information to help improve code in the future and help developers understand the issue behind the specific code quality finding. All right, and that's it. So Cougar is available today. You can get started at this website. I'd love to hear feedback from folks, and feel free to send any questions my way. All right, thank you very much.
Awesome. Thank you, Lee. We are a little ahead of schedule, so if anybody wants to join or type in a question or turn on their audio and ask a question, we can take one. Okay, so
everyone's saving themselves for the Q&A afterwards.
Yeah. So, I mean, if somebody comes up with a question in the meantime, they can. But Nathan Chong is next. We're going back down in the bits of the bowl of everything. And so Nathan is also a principal scientist. He's working on proving memory safety, thread safety for low-level code, and he's going to talk to us about his experiences and applying it to IoT and other applications. So take it away, Nathan.
Hey, thanks, Neha. And hello, Cav. It's a privilege to tell you about how we're applying separation logic to the FreeRTOS kernel. So what is FreeRTOS? It may surprise you to learn that even if you're unfamiliar with the project, you may still have interacted with it. Here are some fun examples, both products containing FreeRTOS inside. So you see, on the left in this smart plug, FreeRTOS may have made you some coffee, or in this oven, baked you some fish. And that's because FreeRTOS is a real-time operating system for microcontrollers, which in another way of putting it is to say that FreeRTOS is an ideal building block for devices in the Internet of Things or the IoT. And this, of course, is where we're trying to disperse computation as widely and as finely as possible so that we can begin to sense and actuate the world at large. And although the examples that I gave were all in the consumer domain, the vision for the IoT is vast. There's a great talk at AWS reInvent 2019 where Volkswagen speak about how the IoT is fundamentally transforming how they're building cars. And that's really why it's so exciting to be applying automated reasoning to FreeRTOS, because this is an incredibly widely used code base with the potential to be deployed to billions of devices. So this is a block diagram of a fairly typical IoT stack. Hardware is at the bottom, and the application-specific logic is at the top. These are going to differ dependent on the domain of your IoT device. FreeRTOS is the set of common functionality in the middle, and it's both the portable abstraction layer of the kernel and a set of common features for functionality like network connectivity. So I'm focusing just on the kernel, but this is just one of many pieces of automated reasoning that we're doing with FreeRTOS. And if you'd like to hear about those, I really encourage you to reach out in the chat to ask about those. All right, then, so let's zoom into this kernel then and talk about the primary data structure that can be used for inter-task communication, which allows for sending and receiving of data between different tasks. And this is the kernel queue that you see here. And interestingly, this has to work in a concurrent setting, meaning that we can have multiple writers, multiple readers, arbitrarily sending and receiving, and that these operations can overlap in time. So there are many interesting aspects to this data structure, but let me highlight one, which is this concurrent setting with tasks, which are entirely standard to the C consistency model, but also interrupt service routines, or ISRs. These are pieces of code that run in an event-driven manner when some hardware interrupt occurs. A good example of an interrupt would be the wake word of an IoT device. And ISRs can themselves interact with the queue. And that's interesting from our point of view because tasks and ISRs are asymmetric in their power. You see, there are things that tasks can do, for example, block, that an ISR must not. And so from a specification point of view, we need to be able to adequately deal with both of these types of user. So we're talking about 700 lines of C code being designed for these microcontroller resource-constrained environments, where we may only have a few hundred kilobytes of memory. And this means that we won't necessarily have features which you would expect in microprocessors. Virtual memory address spacing, for example, isn't normal in microcontroller environments. By low-level coarse-grained concurrency, I mean that these mechanisms are really close to the machine. So, for example, the main mechanism that we're going to acquire a global lock on the queue is to turn off interrupts. On the other hand, our requirements for what we prove about the kernel queue are quite deep. We want to have memory safety, we want to have thread safety, and we want to have functional correctness. And we want this over the code of the implementation, not just the model. So separation logic's a great fit for this because fundamentally we're reasoning about resources and ownership. And then within the space of tooling available to us, we want to explore the more automated end. Verifast is such a tool. It's from Bart Jacobs and his colleagues at KU Leuven, and it's a deductive verifier for separation logic built using symbolic execution. Verifast has been applied to a number of really interesting industry projects, including Java card programs and Linux device drivers. So we were really keen to try it out too. And I think it's time that we took a look at some code together. So let me first point out that FreeRTOS is developed under an MIT license and freely available on GitHub. The same is true for the proofs that I'm going to show you. Let me show you that Verifast absolutely lives up to its name. Here we're going to run a proof regression over those 700 lines of implementation, 20 functions in total. We're going to be checking memory safety, thread safety, and functional correctness in about 4 seconds. Finally, let's peel back the layer one more level and look at a proof in a little more detail, just to give you an essence of what it looks like. This is the Verifast IDE, and the green bar at the top shows that the proof was successful. The proof itself is for an internal function to the Queue API. And it's called by the send operation when we want to put the contents of this buffer here into this queue. And ultimately, if we scroll down in the implementation, we see that this is done in the implementation as a memcopy call. So we see in the function contract, in particular in the precondition, the separating conjunction of separation logic is essential to ensure that the source and the destination of that memcopy are disjoint. In other words, ensuring that the memcopy is well defined. Moreover, we are able to express in Verifast user-provided predicates. And this is a shape predicate that captures the well-formedness of the queue. And in particular, it allows us to lift the concrete implementation of the queue into its abstract representation, the logical list of elements inside the queue. This is best seen inside the post condition here, where after appending to the back of the queue, we see that the resulting data structure, its logical representation is the original contents of the queue, abs, plus this new element x, where x is indeed the symbolic contents of that buffer that we wanted to enqueue in the first place. So I hope this gives you a flavor of what it's like to work inside Verifast. And I'll add that this speed that we saw in the proof time was really valuable when we were developing the proofs for having rapid feedback. Let me finish with a quote from Richard Barry. He's the founder of the FreeRTOS project and a senior principal here at Amazon. And I asked him to comment on the work to apply separation logic and all the other pieces of automated reasoning that we're doing too. And he said, quote, demonstrating due diligence through the use of these state-of-the-art best practices is essential to maintain the confidence and trust of our user base. And well, I just love this quote because any world in which separation logic is starting to be seen as best practice is a really great one indeed. And I think in no small part to the work inside this community. So on that very positive note, I'll leave you there. Thank you.
Awesome. Any questions?
I'll have a look in the chat and follow up.
Cool. Well, thank you, Nathan. Very exciting. Touching all parts of our life, whether we know it or not. Coming on to the next one, some of you may know the speaker. His name is Daniel Kroning. He's attached to Cav in some ways, more than one, I'm told. But he recently joined Amazon as a full-time employee. So we are very lucky to have him and actually talk about some of his work. So welcome, Daniel.
Thank you very much, Nam. So what you've seen is Lee presenting work on how to use machine learning techniques in order to verify software. Okay, so the idea there is that we improve what we're doing to deliver our usual targets, which is to verify hardware, software, and similar things by means of machine learning. So I'm going to flip that around. And what I'm going to explain to you how the things we already know, so meaning the techniques we have been using in the last 30, 40 years or so, will help us to improve machine learning. Just for a bit of context here, one of the things I've done was in my career was a postdoc with Ed Clark at Carnegie Mellon University. Okay, and Ed Clark was always extremely welcoming of customers, of verification and model checking in particular. So anyone who came and said, like, I heard you're doing this temporal logic model checking business, and it could be useful for my application. His first answer, even before he heard what the application was yes, okay? And he was always very welcoming of anyone who wanted to use verification for more or less any purpose. This worked out in some cases extremely well. So a very, very high profile example is hardware verification. And it's absolutely fair to say that any hardware engineer anywhere on the planet that builds circuitry will have heard of formal verification and model checking. and you can go into any semiconductor company and ask them how they assure correctness of a circuitry, and the answer will very often involve off-the-shelf formal verification tools, model checkers that they in essence buy from the EDA industry. Okay, so this story did go on. So we have Byron on the call, and he can tell you a lot how the progression of the adoption of software analyzers happened in places such as Microsoft and in many other companies. I don't think we're quite there yet. We are not yet at a point where we can credibly say that each and every software engineer on the planet will necessarily assume that model checking is a tool that they use on a daily basis. Okay, but there's certainly been quite some progress. So verification has over the years engaged with many other areas. So I would say that in security, verification technology is something which is certainly acknowledged to be something that's useful to prevent exploitable security vulnerabilities. But there have been also other interactions with many research areas, for instance, biology, or so very recent applications, for instance, include, for instance, the analysis of legal text and whatnot. My view is that machine learning is one of these applications. So it's somebody who wants to know something about their design, okay, with various goals in mind. So a very common goal is that you feel that you might have to improve it, or that you want some reassurance that it does what you intended. Okay, so what I'm looking at is whether we can explain what trained components are doing, and whether we can get assurances about them, and perhaps we can find one or the other bug that will then let us eventually fix it. So the key thing I'm interested in is how to do that at scale. So size matters here. So we have seen early work in our community where we have turned neural networks into SMT formulas. This is entirely feasible and something relatively straightforward to do with translation. A neuron in a neural network is in essence an if, okay? So it's an ITE expression in SMT-lib. And then you would have a linear expression followed afterward. So we have done that, and it didn't scale to a level.
Daniel, are your slides supposed to be advancing?
Not quite yet. I will get there.
Okay.
I will get there. So back to the point of scale. Okay. So a neural network of realistic proportion will have 1 million neurons, possibly 2 or 3 million neurons, okay? Whereas the capacity where we're currently at with our formal reasoning techniques might be in the order of a couple of hundred. So there's a big gap in terms of what where we need to be at and what we can currently do, okay? Furthermore, a lot of the traditional QA processes that the software industry has adopted in the past 50 years or so don't work terribly well for trained components. And what I'm referring to here isn't model checking, but testing processes. Let's say the QA stack that Jim has mentioned earlier. Okay, so if you apply this to a trained component, it doesn't quite provide you with the same level of reassurance that you normally get from using this sort of technologies. And among all trained components, deep neural networks are particularly problematic and difficult to deal with. In particular, behavior of these sort of components may be surprisingly frail. So this means it has worked for you many times when you looked at it, and you turn around, okay, you turn your back to a computer, and then it starts failing and misbehaving and doing things that you didn't quite expect to do. The usual answer in the community to that problem is do validation. So this means collect a lot of data where you know the answer, okay? Then you're not supposed to use that data to train, but what you're supposed to do with that data is to check if the if the software that you're building would deliver the expected answers on that validation data set. Okay, so how can we help? Okay, as the community that is used to building verification technology, I'm just going to give you pointers or teasers, rather, to pieces of work that has been published in this area. So this is about the idea of using a trained neural network to produce test inputs. Okay, specifically adversarial inputs. This means these are inputs which would trigger a neural network to deliver a wrong classification or labeling, whatever you want to have it. So basically just giving you some flash images here. What we have on the left is an image which is correctly classified, in this case as the Alps, and on the right-hand side it's classified as a bison, okay? Down here, what we have is a sea snake, which turns into a crossword. So I should stress that all of these inputs have been generated automatically by tooling that's obviously designed in order to produce inputs of this case. Yeah. So on the right-hand side, we have more technology. So we turn the robin, the bird into a keyword. So again, these images are generated. Yeah. Here's another piece of work which is going to be presented at ECCV, which is a vision conference. Now, suppose you have a neural network that, in this case, performs classification. How can you tell what it really does? Okay, so I'm now considering the case where the neural network delivers the expected answer. So you might be under the impression that it's doing just the right job. Okay. So what we see here is a dog. The dog got labeled as a dog, so everything is all right. But why is it a dog? Okay, and what this technology that I'm showcasing here is doing is it will give you a minimalist reason as to why it's a dog. So a reason in this case is a subset of the input. So everything that's in gray here has been masked out. And the remainder of the picture, so in this case, the head of the dog still gets classified as a dog by the neural network. Okay, so in this case, this worked out reasonably well, and we would say, well, you know, the reason why this picture is a dog is because of this part here. Okay, we might have been happy with maybe some lower parts as well, but definitely would have been unhappy if it used this toy here as a reason why it's a dog. But then on the other hand, look at this image here. So yes, it's correct in the sense that the boy is wearing a cowboy hat, so the classification isn't wrong, so it will pass your validation. But the reason that the neural network uses to classify it as a cowboy hat is maybe not what we would intuitively expect. So what we see is that this subpart of the image here, which is clearly the boy's face and has nothing to do with the cowboy hat, is the key reason why the neural network decided that this is a cowboy hat indeed. Okay, and that clearly points to a problem with either the setup of the training or the data set that you've been using. In any case, that's something that needs to be fixed. Okay. So here we have some data, and one of the things I want to do is just point at is a timeline here. So these are competing tools that use other kinds of technology. So what is interesting is the progression in that field. So what we see here is the size of the explanation, so meaning how many of the pixels do you have to put into the subset of the image before the neural network will classify your image with the right label. So obviously this has a point here where if you give it the entire image, it will definitely classify it the way it does, okay? And there's a point down here where if you give it nothing, it would be highly surprising if it gave the right classification. And then there's something in between, okay? So as you grow your explanation, as you grow the subset of the image, you would expect to see more and more correct explanations. So SHAP was a tool that was pioneering in this area, and as you can see, you need to give it a pretty large part of the image before it produces not even half of the labels correctly for your data set. So we are really nearly approaching 100% here. The tool that produced the explanation that you've just seen is called DeepCover. So that's the blue line here, as in Oxford blue, of course. Okay. And as you can see, with a relatively modest fragment of the image, so something like a third or so, you get a very large number of the images classified in the way you would expect. So what I did want to point out is there's a couple of other tools, Rise, GradCam, Lime, and so on, Extremal, who've been published very, very recently in the last 6 months to a year or so. And as you can see, these are getting closer and closer to the performance of deep cover. So there's massive and very rapid progress in this area of research. So just to give you an idea of what sort of the difference could be between tools or algorithms. So what you see here is a number of samples taken from the classifier. So N is the number of times you query a neural network. And then you see the resulting explanation being given. So on the right-hand side, you have RISE, which is one of the competing tools. On the left-hand side, you have Deep Copper. On the very left, you have the original image. So one cool thing about doing research around image classifiers is that you get to use cute images of puppies and kittens and strings. Okay. So what we can see here is that for 2,000 samples, we get a fairly decent explanation. For 200, which is very, very small amount of compute used, we still get a pretty decent explanation of what's going on. On the other hand, if we let RISE only have 200 samples, then you can see it starts using pieces of the grass and so on. That's the explanation, which is clearly not correct. Okay. So I will end things here with just a bit of advertisement. So these are the references to our work that I've just mentioned, and also to others. So you can also look at neural networks that control an agent, for instance. So meaning they evolve a system over time. So we've looked at work where we asked the question whether such trained agents would satisfy LTL properties, and how would you do that effectively with acceptable amounts of compute. We've also looked at the question whether giving specifications in temporal logic would let you train better agents, so meaning produce, for instance, a multi-headed neural network, which splits phases of the job that needs to be done, and similar things. So I'm very happy to send pointers to further work in this area if anyone has questions about it. Thank you.
Thank you, Daniel. Well, as usual, fire away questions for Daniel in the Chime chat, and we are a little ahead of schedule, but we'll keep going. We'll keep powering through. Last but not least, we have Byron Cook, who started the automated reasoning group about 5 years ago at Amazon, and he's going to talk about some of the exciting new things that he's working on himself. He's been in his I'll say basement, even though he's technically on the second floor. It's a more powerful image. He's been in his basement hacking away, and so I'll yield the floor to him for him to tell us about it.
Yeah, awesome. Can you see my screen and can you hear me?
Yes, we can hear you now.
Good. Awesome. So this is my name. I'm Byron. Here's my email address, Byron at Amazon. It's pretty easy to remember. So here are some tools we know and love. Perhaps you've used them. And the thing about these tools, and basically all of the tools that we use in our community, is that they're built with the assumption that you're running on a single computer. They're typically built by someone who ran them on a laptop, and they ran them very effectively, and they have deep understanding of the tool, or the tools have made a bunch of decisions based on the assumption that they're running on a single computer. And so, for example, if we look at SVComp and look at the environment in which contestants are competing, we're limited to 8 processing units of CPU. And so the question emerges today is why do we have this limitation, right? Because the thing is, aside from the formal methods community, everyone else has moved to massively distributed systems. So the entire world, if you look at all of the customers of cloud, they're running massive distributed systems across thousands, tens of thousands of computers. So there's for example, in AWS, we have a global and exponentially growing amount of compute resources available in the cloud. Currently, there's 24 regions. There's 3 new regions that have been announced. And then in each region of the world, there's multiple what they call availability zones. So there's 77 availability zones currently worldwide. And this is a slide. I mentioned this in my Flock plenary talk 2 years ago, but it's worth mentioning because it gives some idea of the scale. So in 2015, AWS, that's Amazon's cloud offering, added enough capacity every day to run all of Amazon.com in 2005. So that's enough new computers to run a Fortune 500 company every day, and that was in 2015. And what we've seen since 2015 is continued exponential growth. So every year, essentially, AWS has grown 50% year over year. So you could take this number and then take 50% year over year over the next 5 years to sort of work out some idea of how many computers we're adding every day into AWS. So we have compute, and we have databases, and we have storage, for example, and all of these are distributed compute and storage services for various performance characteristics you need. So, for example, if you need state, you would one of the good services for very fast, distributed, eventually consistent state is DynamoDB. Another example would be queues. So SQS, called the Simple Queue Service, is a queue API that's distributed and eventually consistent. And then we have both serverless and server-based computation. So if you want 1,000 Linux machines in the sky, you use EC2. And if you just want to pass code to a service and you have no idea how it's operating that or on exactly what kind of computer it's operating on it, then you'd use Lambda, for example. So the question that has been emerging in my head since joining Amazon is like, why would you write proof search programs for this computer, a laptop, when you could write programs for this computer, right? This is a big computer that we can program, right? So we can have distributed algorithms looking for a single proof over thousands of computers, and we can find eventually consistent invariants or eventually consistent proofs for a single problem. And one of the charming aspects of mathematical proof is it's only the final argument that really matters, right? You can do complete voodoo along the way and add case splits as you like. You could base your reasoning based on flawed assumptions, but so long as in the SAT solver you eventually find a proof that holds by the proof system in the SAT solver, or in a symbolic model checker, if you find an inductive invariant, right? That could be the representation of the BDD, the interpolants you find, what have you, then no matter how you got there, so long as ultimately you have a proof, then you're done. And so you can distribute that search over many machines, and they may be out of sync as they're doing proof search, but so long as it converges eventually into a consistent inductive invariant, then that's all you need. That's all you really need to care about. So the validity of induction or the SAT instances can be proved typically in linear time, very easily, independently, and actually in parallel, separately, right? So it's the act of finding a proof and checking your proof are really independent, and they can both be done in a massively distributed way. And then if you look at many of our symbolic algorithms, and I should point out that the concrete algorithms, like say like explicit state model checking, has been making use of distributed systems and concurrency for some while, but in the symbolic reasoning area, we're quite behind. But actually, many of these algorithms are sort of ready for distribution with a bit of work. So if we take, for example, Ken's paper from Cabo 6, he's describing a tool called Impact, and this is sort of the ultimate interpolation-based symbolic model checker. So what Ken does is he introduces, here I have from figure 4 of the paper, there's a few other operations, but basically 4 operations that you can execute in any order to find an inductive invariant over the program, right? And so we're built in Ken's paper. What he's doing is he's unfolding the control flow graph into a tree and then trying to limit the space of the growth of that tree by finding back edges which represent the current candidate for an inductive invariant. And there's no reason that this needs to be executed on a sequential machine. In fact, there's no reason this needs to be executed on a machine. You can imagine many different machines all editing this graph. And so long as we eventually find a consistent proof by induction, then we're done. So with a bit of care, we can call, expand, refine, and those cover steps, and there's a few other steps in Ken's paper, on many machines in an eventually consistent graph, and now distribute perhaps in you get speed ups that are linear with respect to the number of processors you use. Who knows? And so another really promising result is I don't know if you're following the SAT competition, but there was a new track in the SAT competition this year called the Cloud Track. And the new cloud solvers, so these are distributed, eventually consistent solvers, are solving problems that none of the other solvers can solve. So there were 250 instances where no sequential solver could solve them in 3,000 seconds, but the cloud solvers, which distributed the proof search and SAT over many machines, were able to solve them. So some questions going on in my head. What are the proof techniques that we need that take advantage of the world's largest and fastest growing computer? Right. So that's a question that's been going through my head, and now I'm taking some time to try and build that. What are the assumptions that are perhaps no longer relevant? Maybe lazy, for example, the lazy loop, right, where you sort of counterexample guided abstraction refinement, or the method of abstracting from theories to SAT. Maybe that sort of works really well in a unit processor or a single machine case, but maybe that doesn't make as much sense in a distributed model. Now, I'm not sure. And so what if we were to take a clean sheet of paper, called like an A4, and try again, but with in mind the we're gonna, the construction of proof certificates is a feature from day one, and also that we're going to always execute this on a distributed global machine, right? And if those are the constraints now, as opposed to we're going to run this really on a Pentium microprocessor really fast, then there's really a different set of decisions we're probably going to make, and that's something I'm working on now. And so I think I'm the last speaker, so I'm now going to end my talk there, and I'm happy to take questions both about this thing I've been talking about, but also I'd be happy to take questions about formal reasoning in Amazon more generally. Thanks.
Thank you, Byron. Questions, comments?